The National Electrical Code, or NEC, specifies approved methods for protecting the grounding electrode conductor, or GEC, from physical damage. According to NEC Section 250.64A3 titled Protection of GEC in Bonding Conductors, the grounding electrode conductor and any bonding conductors routed outdoors must be protected from physical damage by one of the following methods. Firstly, protection can be provided by a raceway or enclosure with openings not larger than permitted by Table 300.1 phone, provided that the raceway or enclosure is located above finished grade or in a concrete floor. Secondly, the conductor can be buried or embedded in earth not less than 12 inches deep. Thirdly, the conductor can be routed so as to minimize the likelihood of its being damaged. This means that polyvinyl chloride conduit, electrical metallic tubing, and rigid metal conduit are all acceptable materials for protecting the grounding electrode conductor from physical damage, as long as they meet the requirements outlined in NEC Section 250.64A3. When selecting a suitable protection method, several factors should be considered to ensure compliance with the NEC and maintain the integrity of the grounding system. Let's examine some crucial aspects for each approved protection method. Regarding raceways and enclosures, if a raceway or enclosure is used, verify that the openings do not exceed the dimensions permitted by Table 300.1. This table specifies the maximum size of openings allowed in raceways and enclosures to prevent the entry of foreign objects and maintain electrical safety. Additionally, confirm that the raceway or enclosure is located above finished grade or embedded in a concrete floor. This requirement ensures that the protection method is not exposed to physical damage from external elements or traffic. The intent is to prevent the raceway or enclosure from being easily damaged, which could compromise the protection of the grounding electrode conductor. As for direct burial or embedding, if the grounding electrode conductor is buried or embedded in the earth, ensure that it is at a depth of not less than 12 inches. Burying the conductor at this depth provides a reasonable level of protection against physical damage from digging, landscaping activities, or other disturbances. It is essential to follow local regulations and codes regarding the burial depth of electrical conductors to ensure compliance and safety. When minimizing damage likelihood by routing, if the grounding electrode conductor is routed in a way that minimizes the likelihood of damage, carefully consider the location and surrounding environment. Avoid routing the conductor in areas where it is likely to be exposed to physical damage, such as heavy traffic areas, construction zones, or areas prone to vandalism. Instead, choose routes that are protected by structures, barriers, or other means to minimize the risk of damage. Now let's dive deeper into the specific conduit types. Starting with PVC conduit, PVC, or polyvinyl chloride conduit is a non-metallic raceway commonly used to protect electrical conductors from physical damage and environmental factors. It is lightweight, easy to install, and resistant to corrosion, making it suitable for various applications, including underground installations. When using PVC conduit to protect the grounding electrode conductor, ensure that the conduit is listed and labeled for the intended use. This ensures that the conduit meets industry standards for safety and performance. Select the appropriate size of PVC conduit to accommodate the grounding electrode conductor, considering the conductor's diameter and the conduit's fill capacity. Follow the manufacturer's instructions for installing PVC conduit, including proper joining methods and support requirements. Next is EMT conduit. EMT, or electrical metallic tubing, is a thin-walled metallic raceway commonly used to protect electrical conductors in exposed or concealed locations. It is lightweight, easy to bend and cut, and provides excellent protection against physical damage. When using EMT conduit to protect the grounding electrode conductor, ensure that the conduit is listed and labeled for the intended use. This ensures that the conduit meets industry standards for safety and performance. Use appropriate fittings and connectors to join EMT conduit sections securely. These fittings must be listed for use with EMT conduit and provide a reliable electrical connection. Properly support EMT conduit to prevent sagging or damage, using straps or clamps spaced according to the NEC requirements. Lastly, let's examine rigid conduit. Rigid metal conduit is a heavy-walled metallic raceway commonly used in applications where maximum protection against physical damage is required. It is made of steel or aluminum and provides excellent mechanical strength and durability. When using rigid conduit to protect the grounding electrode conductor, ensure that the conduit is listed and labeled for the intended use. This ensures that the conduit meets industry standards for safety and performance. Use threaded fittings and couplings to join rigid conduit sections securely. These fittings must be listed for use with rigid conduit and provide a watertight and corrosion-resistant connection. Properly support rigid conduit to prevent sagging or damage, using hangers or clamp space according to the NEC requirements. In addition to selecting the appropriate protection method, several other considerations are essential to ensure compliance with the NEC and maintain the integrity of the grounding system. Verify that the grounding electrode conductor is sized correctly according to NEC Table 250.66, based on the size of the service entrance conductors. Use listed and labeled connectors and fittings to connect the grounding electrode conductor to the grounding electrode and the service equipment. Ensure that all connections are made tightly and securely to provide a low impedance path to ground. Protect the grounding electrode conductor from corrosion, especially in harsh environments, by using corrosion-resistant materials or coatings. Inspect the grounding electrode conductor and its protection method periodically for signs of damage or deterioration. Repair or replace any damaged components promptly to maintain the effectiveness of the grounding system. Remember that the primary function of the grounding electrode conductor is to provide a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. A properly installed and maintained grounding system is essential for protecting people and equipment from electrical shock and fire hazards. Grounding electrode conductor should be unspliced. The 2023 NEC in 250.64 cone addresses the topic of splicing grounding electrode conductors. Grounding electrode conductor shall be installed in one continuous length without a splice or joint. If a grounding electrode conductor is installed, it needs to be a continuous run. The exception allows irreversible compression type connectors listed as grounding and bonding equipment or by the exothermic welding process. The grounding electrode conductor is permitted to be spliced only by irreversible compression type connectors listed as grounding and bonding equipment or by the exothermic welding process. Now let's discuss an overview of grounding electrode systems. A grounding electrode system is a network of interconnected grounding electrodes designed to provide a low impedance path to earth for electrical systems. Its primary purpose is to stabilize voltage, facilitate the operation of overcurrent protection devices, and minimize the risk of electrical shock and fire hazards. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, metal underground water pipes, or concrete encased electrodes connected together to form a comprehensive grounding network. Grounding electrodes are conductive objects that are buried or embedded in the earth to establish a direct connection to ground. They provide a low resistance path for fault currents to flow back to the source, allowing overcurrent protection devices like circuit breakers and fuses to trip and to energize the circuit. The effectiveness of the grounding electrode system depends on several factors, including the type and number of grounding electrodes used, the soil conditions, and the quality of the connections between the electrodes and the electrical system. Proper installation and maintenance of the grounding electrode system are essential to ensure its reliability and effectiveness in protecting people and equipment from electrical hazards. Ground rods are perhaps the most common type of grounding electrode. Ground rods are typically made of copper-clad steel or stainless steel and are driven into the ground to establish a direct connection to earth. They come in various lengths and diameters, depending on the soil conditions and the required grounding resistance. To install a ground rod, drive it vertically into the ground until its top is flush with the surface. In some cases, the ground rod may be driven at an angle if obstructions prevent vertical installation. Multiple ground rods may be required to achieve the desired grounding resistance, especially in areas with poor soil conductivity. Ground plates are another type of grounding electrode. Ground plates are typically made of copper or zinc and are buried horizontally in the ground to provide a large surface area for contact with the earth. They are often used in areas with rocky or sandy soil where driving ground rods may be difficult. To install a ground plate, dig a trench at least 30 inches deep and place the plate horizontally in the trench. Fill the trench with soil and compact it to ensure good contact between the plate and the earth. Metal underground water pipes can also be used as grounding electrodes. Metal underground water pipes can serve as effective grounding electrodes due to their extensive contact with the earth. However, certain conditions must be met to ensure their suitability for grounding purposes. The water pipe must be metallic and in direct contact with the earth for at least 10 feet. Plastic or insulated sections of the water pipe may compromise its effectiveness as a grounding electrode. The water pipe must be electrically continuous and free from any insulating joints or coatings that could impede the flow of fault current. A bonding jumper must be installed around any insulating joints or sections of the water pipe to maintain electrical continuity. It is important to consult with a local water utility and electrical inspector before using a metal underground water pipe as a grounding electrode. Some water utilities may have restrictions or requirements regarding the use of their pipes for grounding purposes. Concrete encased electrodes are another type of grounding electrode. Concrete encased electrodes, also known as U for grounds, are grounding electrodes encased in concrete foundations or footings. They consist of a length of bare copper conductor encased in at least 2 inches of concrete and placed near the bottom of the foundation or footing. Concrete encased electrodes provide a very effective grounding path due to the large surface area of contact between the copper conductor and the concrete. They are commonly used in new construction projects to provide a reliable grounding system for the building. The bare copper conductor must be at least 20 feet long and at least 1/2 inch in diameter to qualify as a concrete encased electrode. The conductor must be encased in concrete that is in direct contact with the earth, such as the foundation or footing of the building. Now let's examine the grounding electrode conductor. The grounding electrode conductor is the conductor that connects the grounding electrode system to the electrical system. It provides a low impedance path for fault current to flow from the electrical system to the grounding electrode system, allowing overcurrent protection devices to operate and clear the fault. The grounding electrode conductor must be sized according to the requirements of the NEC based on the size of the service entrance conductors. It must be made of copper or aluminum and must be protected from physical damage and corrosion. The grounding electrode conductor must be connected to the grounding electrode system using listed and labeled connectors and fittings. The connections must be made tightly and securely to provide a low impedance path for fault current. The grounding electrode conductor should be run in a straight line as possible, avoiding sharp bends or kinks that could increase impedance. It should be protected from physical damage by routing it through conduit or other protective measures. The grounding electrode conductor should be connected to the electrical system at the service equipment, such as the service panel or main disconnect switch. The connection should be made to the grounding bus or neutral bus in the service equipment. The grounding electrode conductor should be identified with green insulation or marked with green tape or paint to indicate its purpose as a grounding conductor. Now let's discuss the purpose of bonding. Bonding is the process of connecting together all metal parts of an electrical system to create a low impedance path for fault current. It is an essential part of the grounding system and helps to minimize the risk of electrical shock and fire hazards. Bonding ensures that all metal parts of the electrical system are at the same electrical potential, preventing voltage differences that could cause shock hazard. It also provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to operate and clear the fault. Bonding is required for all metal parts of the electrical system that are likely to become energized, such as metal conduits, metal enclosures, metal raceways, and metal equipment housings. Bonding is typically accomplished by connecting the metal parts together with bonding jumpers, which are short lengths of copper wire or strap. Bonding jumpers must be sized according to the requirements of the NEC, based on the size of the circuit conductors. They must be connected to the metal parts using listed and labeled connectors and fittings. Bonding jumpers should be installed in a way that minimizes impedance, such as by using short, direct routes and avoiding sharp bends or kinks. They should be protected from physical damage by routing them through conduit or other protective measures. Bonding is especially important in areas where water is present, such as bathrooms, kitchens, and outdoor locations. In these areas, all metal parts of the electrical system that are likely to come into contact with water must be bonded together to minimize the risk of electrical shock. Now let's discuss the requirements for supplementary grounding. Supplementary grounding refers to additional grounding electrodes or grounding connections that are installed to supplement the main grounding electrode system. It is often used in situations where the main grounding electrode system is inadequate or where additional protection is needed. Supplementary grounding may be required in areas with poor soil conductivity, where the main grounding electrode system does not provide a low enough impedance path to ground. It may also be required for sensitive electronic equipment that is susceptible to damage from voltage surges or electrical noise. Supplementary grounding electrodes should be installed in accordance with the requirements of the NEC. They should be connected to the main grounding electrode system using grounding electrode conductors that are sized according to the NEC requirements. Supplementary grounding connections should be made to the equipment grounding conductor or to the metal enclosure of the equipment. They should be made using listed and labeled connectors and fittings. Supplementary grounding should not be used as a substitute for proper bonding. Bonding is still required for all metal parts of the electrical system, even if supplementary grounding is installed. Now let's discuss the inspection of grounding systems. Regular inspection of grounding systems is essential to ensure their continued effectiveness in protecting people and equipment from electrical hazards. Grounding systems should be inspected at least annually and more frequently in harsh environments or where there is a history of grounding problems. The inspection should include a visual examination of all grounding electrodes, grounding electrode conductors, and bonding connections. The grounding electrode should be checked for signs of corrosion or damage. The grounding electrode conductors should be checked for proper sizing, routing, and protection from physical damage. The bonding connections should be checked for tightness and corrosion. The grounding system should be tested to verify that it provides a low impedance path to ground. This can be done using a ground resistance tester or a ground impedance tester. Any problems or deficiencies that are identified during the inspection should be corrected promptly. This may involve replacing damaged components, tightening loose connections, or adding additional grounding electrodes. A record of all inspections and maintenance should be kept to track the performance of the grounding system and to identify any recurring problems. Proper grounding is essential for electrical safety. Always consult with a qualified electrician when installing or maintaining electrical systems to ensure compliance with the NEC and local codes.